We talk about valence electrons. The valence electrons are the electrons that are in the largest shells or largest sublevels of the atom, and so they're more on the outside of the atom. These are the electrons that are going to interact with electrons of other atoms. And so the number of valence electrons is going to have a big impact on how an atom behaves. And that's going to affect chemical and physical behavior. So the valence electrons are those in the outermost principal energy level. So if we're talking about the quantum hotel, these are electrons on the highest occupied floor. Oops. Highest occupied floor of the hotel. The group number, turns out, the 1A, 2A, 3A group numbers, corresponds to the number of valence electrons that an atom has for the main group elements. So the valence electrons are the outermost electrons. All of the other electrons together are called the core electrons. You just stick them in the middle, or the core electrons. They don't really matter very much, honestly, in terms of interactions. So if we look at this smaller version of the periodic table, here are the group 1A elements. These all have 1 valence electrons. 2A has 2 valence electrons. Because if we look at the orbital diagram for magnesium, let's draw that real quick. Oops, that's not what I wanted. And I'm going to do it more like the hotel that's vertical. So magnesium has 12 electrons. So they're going to be occupying the rooms like this. There we got 10, 11, 12. So this is the first floor, the second floor, and the third floor. Which floor is the highest that has any electrons on it? The third floor, right? If we number the periods here, we'll see that these are corresponding to the quantum numbers for the s orbitals here. So magnesium has 2 valence electrons. If we go over here, the next one that would fill up would be the 3p. So aluminum has 1 electron in the 3p. And then silicon has 2 electrons in 3p. So silicon is in column 4. How many valence electrons does it have? We're looking at the top floor. 1, 2, 3, 4. It doesn't matter what room they're staying in. How many electrons are staying on that highest floor? It's the valence electrons. Okay? Over here, group 8A, well, helium's too small to have 8 electrons. So, he's one of these guys that does a lot of exceptions. But all the other noble gases all have 8 valence electrons. Group 6, 6 valence electrons. This is one of the reasons I really like the 1A, 2A, 3A numbers rather than the 1 through 18 business. Oh, what I forgot to say is now we can begin to understand the reason for elements in this same column having similar properties. They have the same number of valence electrons, and that affects their behavior. So the noble gases, helium is just, the small version. Its first floor is full. And these guys, the second floor is full, the third floor is full, right? So these guys have similar properties because their highest occupied floor is full of electrons. And that does something. Okay, let's write an electron configuration for phosphorus and identify the valence electrons and the core electrons. phosphorus. How many electrons? 15. I'm going to draw an orbital diagram here as well, just because, well, I like them. So 15 electrons. Go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And these rooms, these sublevels have names: 1s, 2s, 2p, 3s, and 3p. So far we're staying in the smaller elements where the ordering makes sense. We'll get to the crazy ordering later. So this is an orbital diagram, and then it's much easier to write the electron configuration looking at the orbital diagram. So in the 1s room, there are 2 electrons. So 1s2. In the 2s room, there's 2 electrons. In the 2p room, how many electrons? 6. 3s, 2, and 3p, 3. So this is the electron configuration for phosphorus. Okay? The valence electrons. We have to think about, well, what's the highest principal level that has electrons in it? What's the highest floor on the electron of the hotel that's occupied? It's the 3rd floor, right? And so everybody on the 3rd floor is a valence electron.
Oh, so it's not just the one that's unpaired.
Yeah, it's not just these guys that are unpaired. It's not just the ones that are in the most expensive room on that floor. It's everybody on the floor. Yeah. So we've got 2 plus 3, which equals 5. I often call them VE, valence electrons. What group number is phosphorus in? Group 5. Group 5, 5 valence electrons. Now, what are the core electrons? Everything else. So all of these guys. And you could identify the number of them by adding these numbers up. Or you could just take 15 and subtract the 5 valence electrons and say, well, there's 10 core electrons. That's supposed to be dark yellow. Any questions? This kind of stuff is a lot more important than the stuff in Chapter 8. But we can't really talk about this stuff without knowing at least a little bit the stuff that was in Chapter 8, right? Because otherwise, what the heck is an orbital? Of course, you still might be thinking that, right? But at least you've heard someone talk about it. Right? Okay, so I told you that this ordering is hiding in the periodic table. So we can divide the periodic table into 4 different blocks that represent those 4 different kinds of sublevels, or 4 different kinds of rooms in the quantum hotel. The group number is equal to the number of valence electrons for main group elements, and the row number for the main group elements is equal to the highest principal quantum number. So that's the floor of the hotel where the valence electrons are. So here, this is the S block, and that's in blue. And you see helium over here. Well, for this purpose, helium really should be over here. Get with the program, guy. Right. Because this is the first level, this is the S room, and there's 2 electrons. And then we go to the 2nd floor of the hotel, and we come to the S room first, and there's 2 electrons there. And then we go down the hall to the P room. So the pink one over here, I don't know if they did this on purpose, but P for pink, or pink P, right? We'll see that there are 6 columns here. And these correspond to the 6 electrons that can stay in a P room because there's 3 orbitals, 2 electrons per orbital, 2 electrons per bed. So then they start to fill up. 2p1, 2p2, p3, p4, p5, p6. Now this is not showing us whether they're paired up or not. We kind of have to look at an orbital diagram for that, but most of the time it doesn't matter that much. And so once the second floor is full, then we go to the third floor. And we hit the S room, and then we hit the 3p room, and then we go to the fourth floor, and we get 4s, and everything's all making sense. And this is where everything gets a little bit wonky because of the penetration and shielding and all those interactions. There was splitting of those sublevels. So we might think, okay, well, this is the D block, right? And this is in period 4, so this is 4D. Yeah, but where did 3D go? The third floor has 3 rooms, S, P, and D. We haven't filled the D room yet. So one way you can kind of think about this is, to me, it kind of looks like it was supposed to be up here. See, now I don't want this guy up there. So it's like going down the steps. And so like this whole block kind of feels like maybe it should be up there. And then it would be 3D. But it sank down. I don't know if that, really helps or not. But the D block elements, this is n minus 1. What's n? Well, this is n over here. So that's the floor number, the principal level. N equals 1, 2, 3, 4. But when we get to the D block, it's 4 minus 1. So this is 3D. This is back to the main group elements. So it's in row 4, it's 4p. And then we come down here and we've got 5s. And then here, this is D again, but it's 4D, because this is row 5 and it's 5 minus 1. So 4D, back to regular, 5p, 6s, and this would be 5D, and then, got to make it a little more interesting here. We're going to jump down to these guys. So I really like that there wasn't space on the wall for the periodic table as it was made. We cut it up and pieced it back together so it would fit above the chalkboard, right? So that's actually what the periodic table is supposed to look like. But it's a bad aspect ratio for a screen or a piece of paper. It's like way too long, right? And these elements are uncommon, and so usually they just like pull them out. This little white area here is where these guys got cut out. And if you look at the periodic table there, you can see where we cut it, right? Just to the left of the word of, there's a little jog there, and you see there's a jog over there. We cut it, and this other part was down below. So here's 6s, and we're going in 1 into the 5D, and then we go down here, because this is 57. We can't go straight to 72. 57, 58. So these are the F block, and so they sunk a little further. And so this is n minus 2. That's the principal. So these are like the S sublevel. There's 2 columns. Here's P. There's 6 of those, and there's 10 of these and 14 of those. I think I misspoke earlier, didn't I? I was talking about there being 10 of these. Yeah, that was wrong. There's 10 of those. This is 14. Because in the F there's 4. There's 7 times 2 is 14. Shoot me now. Were they looking at the periodic table and trying to figure out some way to make the quantum mechanics match up to the shape of the periodic table? No. I just think that's pretty cool. Any questions? So I've seen tricks where you write these things out and then you draw zigzag lines and stuff. or you could memorize the order of filling, but it's right here in the periodic table, right? 1s, 2s, 2p, 3s, 3p, 4s, and then you have to remember this sync. So this is 3d. And this is back to regular, 4p, 5s, sync again, that's 4d. Back to regular, 5p, 6s, right? So it's all hiding in there. So we can use the periodic table to write the electron configuration. So let's look at chlorine, and we're going to do the inner electron configuration for chlorine. So here's chlorine, the element we're interested in. We're going to go up a row and find the previous noble gas. And so, okay, that's neon. And now we're going to write down just the electrons that come after that. So over here, we've got 3s, and there's 2 there, so that's 3s2. And then we jump across here, and this is 3p. 1, 2, 3, 4, 5. 3p, 5. We don't include the d because the d orbitals are more expensive than the p orbitals. They're not going to fill until we get these filled up. And the 4s room is cheaper, and so that's actually going to fill up before these guys. You know, pricing at hotels is weird, right? Why are the rooms down the hall more expensive? Well, maybe because they're further from the elevator and the ice machine and all the noise of people coming and going. I don't know. And we can make this very elaborate if we want to. Any questions? Use the periodic table to determine the electron configuration of bismuth. Well, first order of business is find bismuth. Where'd you go? Oh, there you are. So bismuth is right here. Let's do the noble gas one because it's easier. So we're going to go up to the previous row and go to the end. This is the noble gas that comes just before bismuth. So we're going to start with xenon. So we put this element symbol for xenon in brackets. That is representing the electron configuration of xenon. So we've got up to here, and now we're going to come over here. We're on row 6, right? So we come across here. That's the S block, and that's in row 6, S2. And then we get to this guy, and it jumps down into these guys. Now, you know, things get a little wonky, but what we're going to do is we're going to talk about like if you said, okay, well there's 5d1. Let's just do it this way. There's 5d1, and then we're going down here. So that's 5d1, and then we follow the arrow and we come down here, and this is the F block. What's the quantum number for that F block? It's 6 minus 2, right? The D was 6 minus 1, this was 5D, and this is sunk down more, and so this is 4F. If you don't remember how many electrons can fit in an F orbital, count the rows. The columns. There's 14. So 4F, 14. And then we get back up here. We're back into the 5D, and we're going to go, whoops, went a little too far. We go all the way across the D block. Well, we're not going to put 5D9 over here and have 5D1 and 5D9. We're going to mention all of those together. And honestly, I don't really care if you put it before 4F or after. I will not try to trick you with a question like that on the exam. I prefer after because most of them are after. And so we're going to put the 10 there and not use this one anymore. And then we're into the P block, and this is back to the regular number, the same as the row number. So this is 6P, 1, 2, 3. 6P3. Electron configuration for bismuth. Any questions? This takes a little bit of practice, but this is conceptually one of the least troublesome things, as long as you don't let the fact that we don't really understand it bother you. It's just this really nice pattern I showed you, right? We can follow the pattern, and that's nice. Right, the electron configuration for each of these elements. There's a little practice. So, chlorine. I'm going to find chlorine. There's chlorine. What's the previous noble gas? Neon. And then after neon, what's that? 3, and this is the S block, right? 3S2. And then we're going to come over here. And how many boxes are there? 1, 2, 3, 4, 5. This is the 5th box. That represents the 5th electron going into that level.
We have to include the box.
Yeah. You have to include the box that represents the element. So chlorine has 17 electrons, right? Well, how many electrons are we representing here? Well, we have 10 from neon, plus 2 in the 3S, and 5 in the 3P, and that adds up to 17. So if you were given an electron configuration, you could find 3P5 on the periodic table and say, oh, it's chlorine. Or you could add up the number of electrons and identify it that way. Let's do silicon. So silicon's over here. So again, going up to the previous level, neon is at the end. And then we're going to come in here, 3S2, and 3P2.
Why 2?
Because in this block, this P block is the second box.
Oh, I see.
Yeah.
Yeah.
Yep. It's very, very good to ask those questions. Because once you get your questions answered, then it's going to make a lot more sense. Okay, strontium. Strontium's over here. What's the previous noble gas for strontium? Yeah, I accidentally swiped onto a different page on my iPad. Yeah, so for strontium, we're coming up the previous one and going to the end, so it's krypton. And then after krypton, we just have these guys here. So that is 5, S, 1, 2. And let's do oxygen. So oxygen is up here. Let's skip the noble gas one for this because it's kind of silly, isn't it? Let's just do the whole thing. So we've got 1s, 1, and 2, because again, helium kind of belongs over here, right? So that's 1s2, which could be abbreviated as helium. And then we've got, what's that? 2s2. And 2p, 1, 2, 3, 4. So 2p4. So the other way to write it would be like this. Any questions? So all that's really nice and everything. A bunch of the larger elements have what we call irregular electron configuration. So when we get this splitting that comes up, the 4s and the 3d sublevels are actually really close in energy. The 4s is a little bit lower, and so it usually fills first. But then sometimes they kind of switch rooms around a little bit. So some of the transition metals have irregular electron configurations where that NS, whether it's 3s or 4s, may only have one electron in it before you get into the D room, or it might skip that one altogether. Okay. These electron configurations have been found experimentally, and I'm only going to ask you to remember 2 of them. This is what we expect from chromium, and this is what chromium actually gives us. So let's look at what's happening in the electrons past argon. So we've got 4s, and then next up is 3d. And so for chromium, there are 6 electrons that go in there. So what we expect to happen is that we go 1, 2, 3, 4, 5, 6. That's what the rules say, right? But it doesn't do that. This guy is going to come over here. Well, that's much more symmetrical, isn't it? Now we have 2 of these rooms in the hotel that are half full. Everybody gets to sleep up right side up and have their own bed. That's kind of a bonus situation, right? The other weird one that I want you to remember, I just want you to remember chromium and copper, is copper is, we expect 4s2 3d9. So this is what we expect. But again, what happens is one of the electrons from this room comes up here. And I said, well, why would it do that? I could see the other guy, he's getting his own bed, but this guy is just getting a different bed, still having to pair up. Well, there was a Groupon deal, and if you had a completely full room and a half full room, you got a discount. Turns out the other thing was a Groupon deal too. If your room's exactly half filled, then you get a discount. So most of these irregular configurations can kind of be explained by saying, well, it's better if this one's all full and that one's half full, right? Or you could have something where this is full and that's empty. Or you can have both of them half full, right? So the ones you need to remember are chromium and copper. And You know, there probably will be one question that'll see if you remember those. But that'll be it. Any questions?